If you could somehow strip away the surface of the ocean and like actually see the raw energy underneath, you wouldn't just see this still, flat blue map.
Yeah. Oh, definitely not.
Right. You would see a totally chaotic, churning, incredibly powerful engine. And I mean, it's fundamentally running the entire planet.
Yeah, it really is the engine. And yet, for decades, we've been trying to predict the future of our climate while basically wearing a blindfold.
A massive blindfold.
Exactly. We have been completely unable to track how this planetary engine actually moves in real time.
Well, until today. Because for you, the listener, we have a custom deep dive into a paradigm-shifting piece of research. It was just published on May 15, 2026, in the journal Nature Geoscience.
It's a huge paper.
It is. And our mission today is to explore how a team of scientists figured out how to track the ocean's hidden dynamics, specifically looking at the Gulf Stream. And they did it not by launching billion-dollar hardware, but by using a new AI system.
Right. They're extracting invisible data from old weather satellites we've literally had floating up in space for years.
Okay, let's unpack this, because to really grasp why this is such a monumental leap forward, we have to look at the historical constraints. Like, why is measuring the ocean so hard?
So, measuring the kinematics of the ocean, which is just a fancy way of saying the actual physical movement of water across the globe, has always been this exercise in severe compromise. For a long time, the absolute gold standard from space has been altimetry satellites.
Right, and altimetry is basically shooting radar pulses down at the water to measure the exact height of the sea surface, right?
Yes, exactly.
Because water piles up, and by mapping the topography of the ocean, you can mathematically derive the large-scale currents.
Precisely. You map the hills and valleys of the ocean surface, and then physics tells you how the water must be flowing around them.
Right.
But there is a massive bottleneck with altimetry, and it all comes down to temporal resolution.
Timing.
The timing, yeah. An altimetry satellite only passes over a specific zone of the ocean once every 10 days.
Wow. Which, I mean, in the context of fluid dynamics, 10 days is an eternity.
It's useless for rapid changes, yeah.
You're trying to understand a highly chaotic, rapidly shifting system, but you're sampling it so rarely that you get this massive aliasing. It sounds like we've been trying to monitor a bustling, high-speed 10-lane highway, but we only get to snap one photograph every 10 days.
That is a brilliant way to put it.
Or, we're stuck standing on just one single overpass. You completely miss all the traffic jams, the speeders, the accidents.
What's fascinating here is that your analogy is spot on. Because you only get that snapshot every 10 days, the data has to be heavily smoothed out.
Right, they blur it.
Yeah, they have to. You end up with a highly generalized climatology, so you see the broad, slow-moving river, but you completely miss all the transient turbulence.
The actual details.
Exactly. And without knowing exactly how the water moves, our understanding of the planet's climate regulation has fundamentally been operating on a time delay.
And if you try to solve that timing issue by, say, using coastal radar or physical research ships, you run into the exact opposite problem, right?
You do. You completely ruin your spatial resolution.
Because a research ship gives you incredible real-time data, like second by second, but you are strictly constrained to the tiny geographic footprint of wherever that one single boat happens to be sitting.
Exactly. We have never had a tool that provides both high spatial resolution and high temporal resolution simultaneously across a really large area.
It was always one or the other.
Right. And because of this, our global climate models, the models that dictate our entire understanding of future warming scenarios, have been relying on heavily blurred, infrequent data.
So if the core problem is that we need high-resolution snapshots every few minutes to capture the fluid dynamics, but we obviously can't afford to just, launch a brand new fleet of ocean tracking satellites.
No, that would be billions of dollars.
Right. So we're essentially forced to scavenge. We had to look at what cameras are already up there. Did we have anything looking at the ocean that frequently?
You actually did. Geostationary weather satellites.
Weather satellites.
Yeah. Specifically, a team led by Luc Linane at the Scripps Institution of Oceanography, they looked at satellites like Godey's East.
Okay.
Now, these satellites were designed to monitor atmospheric conditions, tracking cloud cover, storm development, that kind of thing.
So standard weather stuff.
Right. But to do that, they are constantly capturing infrared imagery. They are taking thermal snapshots of the Earth's surface every 5 minutes.
Okay, here's where it gets really interesting, because I have to push back on this.
Sure, go ahead.
A weather satellite is measuring sea surface temperature. It's looking at infrared radiation. How do you get physical velocity, the actual kinetic directional movement of water, from a temperature map?
That is the million-dollar question.
Because, I mean, if you're just looking at a heat map, you aren't seeing the current itself, right? Is it like watching a drop of ink spread out in a glass of water to see the current?
That is exactly what it is. You aren't seeing the current directly, no, but you can use temperature as a passive tracer.
Passive tracer.
Yeah. Imagine your ink drop. If you time exactly how fast that ink spreads, stretches, and deforms over time, you can mathematically reverse engineer the invisible currents inside the glass that are actually pushing it around.
Oh, wow.
The AI is doing exactly that, but instead of ink, it's using heat.
So you're basically reading the invisible wind by watching how the leaves blow.
Precisely. When you look at high-resolution thermal imagery of the ocean, you see incredibly intricate thermal filaments, sharp temperature fronts, and these swirling gradients.
And the AI reads those.
Yeah. The Scripps team built an AI system called GeoFlow, and they trained a neural network using vast, highly complex ocean simulations.
Okay, simulations.
Right. They essentially fed the AI millions of examples showing the precise relationship between a specific current and the resulting spatial gradients of temperature over time.
So let me make sure I've got this. If a pocket of warm water twists and elongates into a specific shape over the course of an hour, the neural network has already learned the fluid dynamics required to create that exact deformation.
You've got it. It looks at the thermal deformation and mathematically infers the shear, the vorticity, and the exact speed of the water moving it.
And it's incredible.
And because the GOSI satellite is taking a picture every 5 minutes, Broslow can process that sequence and output a highly accurate map of water movement every single hour.
Every hour.
Every hour. We go from a 10-day altimetry delay to an hourly live feed.
But wait, I have to challenge the methodology here for a second.
Fair enough.
If you train a neural network purely on simulations, even incredibly detailed ones, aren't you just creating a closed logic loop?
Ah, I see what you mean.
Like the AI is going to find the physics it was programmed to find. How do we know it's not just hallucinating these fluid dynamics when you point it at the messy, unpredictable real world of the actual ocean?
That is the ultimate test of any machine learning model applied to the physical sciences. And it's exactly why the validation phase of the GeoFlow project in 2023 was so critical.
Okay, so they did test it in the real world.
Oh, absolutely. They didn't just run the model and declare victory. They took GeoFlow's hourly maps and tested them directly against real-world in situ data.
Where did they test it?
They went straight to the Gulf Stream.
Oh, wow. Which is, I mean, that's one of the most powerful and chaotic western boundary currents on the planet.
The ultimate stress test.
Seriously.
They compared the AI's thermal inferred currents against actual physical measurements taken by acoustic sensors on research ships that were actively navigating the Gulf Stream at that exact moment.
And what was the result?
The agreement was excellent. The AI was not hallucinating. It was accurately capturing the true kinematic field.
That is wild. And what's really crazy is that the paper notes, it didn't just match the ship data. It completely shattered the limitations of our previous satellite capabilities.
It really did.
Because we suddenly had hourly resolution, the AI started revealing structures that the old 10-day altimetry loops were completely smearing out, specifically these sub-mesoscale structures.
Yes. And this is where the breakthrough transitions from a cool technological trick to a fundamental shift in climate science.
Okay, break that down for us.
In oceanography, the mesoscale refers to eddies and features that are tens to hundreds of kilometers across.
That's some big stuff.
Right, the big stuff. We could see those with altimetry. But submesoscale structures are the intricate, highly energetic swirls and boundary layers that are only like 1 to 10 kilometers across.
Tiny, relatively speaking.
Tiny, and they are born and dissipate incredibly fast.
Which means if you only look every 10 days, they basically don't exist in your data.
Exactly. They vanish into the averages.
But I mean, in an ocean that covers most of the planet, why does a 5-kilometer swirl in the middle of the Atlantic actually matter to the listener? Why do we care?
If we connect this to the bigger picture, it comes down to thermal stratification. The ocean is highly stratified.
It has layers.
Exactly. You have warm, lighter water sitting on the surface, exposed to the atmosphere. And then you have cold, dense water trapped deep below.
Right.
That stratification creates a physical barrier. So if the surface water is absorbing massive amounts of heat and carbon dioxide from our atmosphere, how does that carbon actually make it down into the deep ocean to be sequestered?
Oh, I see. It needs a transport mechanism. It needs something to break that barrier.
Yes. It requires vertical velocity. And these rapidly shifting, highly energetic submesoscale eddies are the primary physical mechanisms that generate those massive vertical velocities.
So they are the agitators.
Exactly. They act as the agitators, subducting that carbon-rich surface water down into the abyssal zone and pulling deep ocean nutrients up to the surface.
So by smoothing them out in past averages, we were completely missing the actual gears of the machine.
We were.
Our climate models have been operating with this massive blind spot. We basically saw the large river moving north, but we missed the millions of tiny vertical vortexes that are actually pulling our carbon emissions out of the air.
Precisely. When we can finally map these submesoscale dynamics globally, it will profoundly recalibrate our understanding of the global carbon sink.
That is massive.
It is. But the implications of GoFlow extend far beyond just long-term climate modeling. Having an hourly, high-resolution map completely transforms our short-term capabilities, too.
So what does this all mean for the listener? I mean, practically speaking.
Well, think about daily weather forecasts.
Better forecast before the morning commute.
Exactly. The ocean and the atmosphere are intrinsically coupled. The exact placement of a warm ocean eddy dictates where atmospheric moisture pools and how storms intensify.
Right, like hurricane rapid intensification.
Yes. When a hurricane passes over a deep, warm pool of water, it acts like rocket fuel.
It just drops the barometric pressure and the wind speeds explode.
Exactly. But because the Gulf Stream is constantly shifting and shedding these warm core eddies, knowing exactly where those thermal energy pools are located on an hourly basis allows meteorologists to drastically improve their models for storm tracks.
That saves lives.
Absolutely.
And it also has massive implications for how we handle marine pollution, like the global crisis of microplastics. Because plastic debris doesn't just spread uniformly across the ocean, it pools together.
It does. Microplastics and other surface pollutants aggregate in convergence zones. And what creates these convergence zones?
Let me guess. The submesoscale boundary layers.
Exactly. The exact structures that GoFlow is now able to map. If we have a live, high-definition map of the ocean's surface kinematics, we aren't just guessing where a massive spill will end up.
We can actually track the specific fronts that act like trash compactors.
Right, which allows us to deploy cleanup resources with pinpoint accuracy.
It really is an unprecedented level of visibility. But, as with all scientific leaps, we do have to look at the limitations. And the source material highlights a pretty glaring vulnerability in the GeoFlow system.
Yeah, there is a catch.
It relies entirely on infrared thermal imagery, right, to track the heat tracers.
Yes, and infrared sensors cannot penetrate cloud cover.
Which is a huge flaw, considering the ocean generates massive amounts of, like, marine stratocumulus clouds. The moment a dense cloud layer rolls in, the AI is effectively blinded.
It loses its passive tracer entirely. It is the single biggest hurdle for this methodology. When the clouds are present, the temporal resolution drops to 0.
So how do they fix that?
Well, the future trajectory outlined in the paper points directly toward multimodal sensor fusion.
Multimodal fusion.
Yeah, combining different types of data. The next step is not to rely solely on thermal imagery, but to combine the high-frequency GOES East data with microwave sensors or traditional altimetry data, which actually can see through clouds.
Oh, that makes sense.
Yeah.
So by feeding all of those different data streams into the neural network, they hope to fill in the missing gaps.
Exactly, to create a truly continuous, uninterrupted global coverage system.
And the most vital part of solving that whole interpolation problem is how the Scripps team actually chose to release this breakthrough. Because they didn't patent the neural network.
No, they didn't.
They didn't lock the data behind some corporate paywall. The code for GeoFlow, the training methodology, the resulting data sets, it is all entirely open source.
This raises an important question about how modern science gets done. By making the code public, Scripps isn't hoarding the breakthrough. They understand that solving the cloud cover limitation is an incredibly complex computational challenge.
Right.
So they are actively crowdsourcing human ingenuity. They are inviting computer scientists, meteorologists, and oceanographers worldwide to just download the model, tinker with it, test it in other currents, and help refine it.
It's a total accelerant for global discovery.
Exactly.
So if we briefly synthesize all of this, we are looking at a monumental shift in how we observe our own planet. We spent decades trapped between the slow 10-day blur of altimetry satellites and the tiny microscopic footprint of physical research ships.
And we completely miss the submesoscale turbulence that actually dictates our climate's vertical mixing.
Right. And the solution didn't require waiting a decade for new space infrastructure. It simply required taking the 5-minute thermal snapshots from weather satellites we've had, hovering above the equator for years.
And teaching an AI to read the invisible fluid dynamics by tracking the deformations in the heat. It stripped away the aliasing and revealed the true, chaotic, vital machinery of the ocean.
It really is a testament to the fact that sometimes the data we need to, save the planet is already sitting right there on our servers. We just haven't built the right lens to look at it yet.
Which leaves us with a really fascinating final thought to ponder. If an AI can extract highly complex vital kinetic energy fields from decades-old thermal weather data just by changing how it analyzes the patterns,
Yeah.
what other massive invisible planetary mechanisms are hiding in plain sight within our existing data archives, just waiting for the right algorithm to finally decode them?
Man, that is a wild thought. Thanks for sharing your sources and diving deep with us today.